Welcome to a session on Virial equation of state. In this session, we will be seeing limitations of van der Waals equation and Virial equation of state. So, both these will be considered in this session. Let us move on to the topic. Limitations of van der Waals equation says that the real gases show deviation from van der Waals equation at low temperatures and high pressure. That is again the same case when the molecular volume is very small. The same problem was met with the real gas equation too, and to modify that, van der Waals equation was introduced, and again even then they show deviations at low temperature and high pressure, and this is because the van der Waals constants A and B, they are not exact constants for a gas, that is for real gases, they do not remain constant and they vary, they do not remain constant, and that is the reason why there is a description in lowering of temperature and increasing the pressure. That is, they vary with temperature. As the temperature changes, the value of A and B keeps on changing for a given gas. So, that is the reason for the deviations observed, and that is a limitation of again van der Waals equation. After all, it is better than ideal gas equation, but not completely applicable for real gases. Now, let us see some problems based on van der Waals equation. First one is using ideal gas equation and van der Waals equation, calculate the pressure exerted by 70.9 gram of chlorine confined in a volume of 5 into 10 to the power minus 3 meter cube flask, that is the volume of the flask, at 300 Kelvin, given that A is equal to 0.659 newtons meter raised to 4 mole raised to minus 1, and B is equal to 5.62 into 10 to the power minus 5 meter cube mole raised to minus 1, and the value of R is given, that is 8.314 joules per Kelvin per mole. This is the atomic mass of chlorine, 35.45. Now, here what we have to see is that we have to find out according to ideal gas equation what will be the pressure, and also according to the van der Waals equation of state, provided they will be giving the units of A and B, but the value of R, it is not necessary that they will give you always the value of R. This suppose that students should know it by heart. So, since all these are in SI units, we have to take, in this problem they have given, otherwise we will have to take the SI units, the value of R, which is 8.314 joules per Kelvin per mole for a gas. Now, here what we are going to do is we are going to take the ideal gas case, which is the first one. PV is equal to nRT. P, the pressure, volume is given. R, we already know, temperature is also given. All these are given, but we do not have the value of N. N is equal to mass by molecular mass. Okay, and here mass of chlorine is given. What is that? Mass of chlorine is equal to 70.9 gram. Okay, this is given, but this is not in SI unit. We will have to convert that into kilograms. For that, what we have to do is 70.9 into 10 to the power minus 3 kilograms. So, that is okay. Now, here we have the value of R, T, V. N is equal to mass by molecular mass, that is 70 divided by. Now, they have given the atomic mass of chlorine. Atomic mass is 35.45, but we all know that chlorine is a diatomic molecule, and therefore, its molecular mass will be 35.45 multiplied by 2. Okay. So, that is what it has been done here, that is mass by molecular mass, that is 70.9 divided by 35.45 into 2, and the value of n is equal to 1. So, we got the value of n. Now, you can substitute these nRT by V, which is equal to, n is equal to 1, R is equal to 8.314 joules per Kelvin per mole, then T is 300 Kelvin whole divided by volume, that is 5 into 10 to the power minus 3 meter cube. Okay. So, everything is there. You are supposed to find out the pressure. That is, I will substitute all these values and solve for it, and you will get the answer as 4.9884 into 10 to the power 5 newtons per meter square. That is, converting the joule factor, you get newtons per meter square as the unit. Again, that is in SI units. Now, we have to go for the van der Waals equation, from which we are supposed to find out the pressure. So, we have terms along with pressure. So, we will have to remove that first, P plus A n square by V square. You are taking V minus n V to the other side, that goes to the denominator, because here it has been multiplied. So, this becomes nRT divided by V minus NB. Okay. Now, taking this term to the other side, we will have P is equal to, since this is added here, it goes to the other side, it becomes subtraction V minus NB minus A n square by V square, taking this term over this side. Okay. So, finally, we have got the equation for pressure from van der Waals equation. Now, we will substitute the values in this equation, and then you can solve for it. The value of n, we have already calculated it. So, no need of calculating that. We have n is equal to 1, R is equal to 8.314 joules per Kelvin per mole, then T is 300 Kelvin divided by V minus NB. V is equal to 5 into 10 to the power minus 3 minus n is equal to 1, and the value of B is 5.62 into 10 to the power minus 5 meter cube mole inverse. This is meter cube. Okay. Minus A is equal to 0.659 newtons meter raised to 4 mole inverse. N square is 1 square, that mole square, whole divided by V square. The volume is 5 into 10 to the power minus 3 meter cube whole square. Now, we will substitute and then solve it. You have to find out the answer for the first term first, and then for the second term subtract it, and finally, you will get the answer as 5.0438 into 10 to the power 5, the unit of pressure in SI units, that is newtons per meter square. Okay. So, you have to be very careful in taking the value of R if not given, okay, and see that all the units are in SI units, even that masses, all those things, length, mass, everything, volume and everything. Okay. So, a similar one, here the units are different. Here calculate the pressure exerted by 1 mole of a van der Waals gas occupying a volume of 15 decimeter cube. 15 decimeter cube is equal to liter at 300 Kelvin. The value of A is equal to 3.0 atmospheres decimeter raised to 6, or it can be liter cube mole inverse. B is equal to 0.05 decimeter cube mole inverse. Here if R, the value is not given, since all these are liters and atmospheres, you will have to convert that the value of R in 0.0821 liter atmospheres per Kelvin per mole. This is what we have to be careful while doing such problems. Okay. So, you have to find out only van der Waals gas equation pressure, what the gas will be showing according to that. So, again we will have to take this as P plus A by V square, taking V minus B to the other side, we have that is equal to RT by V minus B. We do not take N here because it is given that it is 1 mole of a gas. So, I have taken van der Waals equation for 1 mole itself without N, then P will be equal to RT by V minus B, taking this to the other side, A by V square. Okay. Now, we have the expression for pressure. We are going to substitute the data as given, R is given, V is given, temperature is given, A is given, B is given. So, R is equal to 0.0821 liter atmospheres per Kelvin per mole. Okay. Temperature is 300 Kelvin divided by the volume 15 decimeter cube minus B. B is equal to 0.05 decimeter cube. Okay. Then minus A, 3.0 atmospheres decimeter raised to 6 mole raised to minus 2 whole divided by V square, 15 decimeter cube whole square. Okay. Now, substituting that. So, here I have shown that like first term on calculation, you will get a numerical value 16.9862. The second term on calculation will give you 1.333. Now, subtracting that, you will get the answer, that is, since this is in atmospheres and liters, the unit of pressure will be in atmospheres, 15.6532, and that will be the answer for this problem. That is the answer for pressure. Okay. Again you can see that is they have asked only for van der Waals equation and we have derived only for the van der Waals equation. Next we will move on to the Virial equation of states. There have been several equations of states proposed, of which somewhat a general one is the Virial equation of state, and Virial equation of state was proposed by Kamerlingh-Onnes, and for 1 mole it gives an expression in which we have a series of 1 by V terms in different powers, 1 by V terms in different powers. So, the expression is as follows: PV, that is pressure into volume, is equal to R, that is the universal constant, T is the absolute temperature, into 1 plus B by V plus C by V square. See the powers of V. In the first case it is 1 by V raised to 0 and therefore that becomes 1. Second one is B by V, C by V square, D by V cube and E by V, V4, V to the power 4 and so on. Now, when we check this, we call this, so first one is written as 1, the second one, this constant is known as the second virial constant, this is the third virial constant, this is a fourth virial constant, this is a fifth virial constant, and so on. So, the terms above the powers of 1 by v, we have certain alphabets B, C, D, or etc. They are known as virial constants or virial coefficients. Now, this is a function of temperature. It is a function of a temperature and it is characteristic of each gas. From gas to gas, it will be different, and again for a single gas at different temperatures, these values will be different, because in van der Waals constant, the defect we found that, or the drawback was that the A and B was supposed to be a constants forever, but it has been found that the value of A and B changes with temperature for a given gas. So, in virial, it has overcome like this, that is, it is dependent on temperatures, a temperature dependent function, and also it is characteristic of a gas, Okay. The second virial constant B, it represents the contribution due to deviations. It represents the deviation from ideal behavior arising from the interaction from a pair of molecules. So, the second one represents the deviations from molecular pairs. Which are a pairs, that is 2 together, okay, 2 molecules together. So, that is the deviation. Now, the third virial coefficient C represents from the interactions from triplets of molecules, that is 3 together, triplets of molecules, and the succeeding terms we know that it is for the groups of 4, 5, etc. So, usually we know that in practice mostly we will be considering the 2 molecules together, and therefore, in practical applications only we do not have the equation extended beyond C. C is when they are in triplets, that is the maximum case, and after that we do not consider the virial equation, because in practice we do not have such a big clusters to be interacting together. It can be either 2 or 3, that is the maximum possible, which has been noted so far. So, now the coefficient B, that is the second virial coefficient, it is generally negative at lower temperatures. At moderately low temperatures, the value of B is negative. Okay. Now, as the temperature increases, the value increases, becomes 0, and then it becomes positive. So, that is what is told here. The coefficient of B is negative at moderately low temperatures, becomes 0, and then becomes positive as the temperature is increased. So, the value of B is usually 0 at low temperatures, when temperature is low, and as temperature increases, what will happen? When temperature is low, the B is negative. As temperature increases, B becomes 0, and then B becomes positive. So, there are cases when B is negative, then B has got a value 0 and B has got a positive value. So, it changes from negative through 0 to the positive values as the temperature is increased. Now, there is a consequence from that, the second virial coefficient B is 0 for a gas is known as the boil temperature. The temperature at which the second virial coefficient for a gas is 0 is known as boil temperature, and it is generally represented as T with a capital B as a subscript. Okay. At boil temperature, we consider the intermolecular interactions resulting from attractive forces exactly balances the repulsive forces between the molecules in a gas, and therefore what happens is the gas can move about without any attraction or repulsion. I will repeat it. At boil temperature, the molecular interactions, that is, which lead to attraction, that is, attractive molecular interactions, they compensate the repulsive interactions between the molecules. They are compensating, and as a result what happens is the molecules will be moving as if they do not have any interactions between them, and that is, we consider that to be an ideal condition, and that is the temperature at which the gas behaves ideally, and this temperature is known as boil temperature TB. Okay. So, for a certain range of pressure it remains as such. Now, the Virial equation of state in terms of pressure is written as a power series of pressure terms. In the other case, it was in terms of volume, in which we have been writing it in terms of the series of 1 by V, pressure and volume inverse proportion. Okay. So, here in that pressure comes to the numerator. So, PV is equal to RT 1 plus B with a single prime P, this stands for pressure. Okay. Then P square C prime P square plus D prime P cube and so on, where B prime, C prime, D prime, etc. are called as the second, third and fourth virial coefficients, which are the functions of temperature and characteristic of each gas. It is not characteristics, it is characteristic of each gas. For each gas it is characteristic, and with temperature it changes. Now, I have given an assignment in which, that is based on the problems we have already solved in this session, that is using ideal gas equation and van der Waals equation, calculate the pressure exerted by 44 gram of carbon dioxide when it occupies a volume of 0.537 liter at 373 Kelvin. Given that A equals 3.6 atmosphere liter square mole raised to minus 2, B is equal to 0.0427 liters per mole inverse, and R is equal to 0.0821 liter atmospheres per Kelvin per mole. See, here R is given, it is not necessary that they should give, since here it is in liters and atmospheres, the unit of R should also be in liter atmospheres per Kelvin per mole. This we will be discussing in the next session. Okay. To conclude, we have been seeing van der Waals equations and its limitations, and it has been found that again when the temperature is low and pressure is high, van der Waals equation shows deviation in the case of real gases, just because the van der Waals constants A and B are not constant for real gases. It shows variations, and therefore they show a deviation. And there are many equations of states, but out of that a most general one is which is proposed by Kamerlingh-Onnes, and in terms of volume the Virial equation of state can be expressed as PV is equal to RT, and we have a factor 1 plus B by V plus C by V square plus D by V cube plus E by V to the power 4 plus so on. Here B is known as the second virial coefficient, this is the third one virial coefficient, this is the fourth virial coefficient, and E is the fifth virial coefficients. And we know that for ordinary gases we do not have virial expression extended after C, because we have molecules in pairs or as triplets, nothing more than that. So, these are the coefficients which represent the deviation of the molecules when the molecules are in pairs that is B. When they are in triplets, it is C, and the D is actually for when they are in 4 in numbers, the other one is 5 in numbers, which is generally not that possible. Now, in terms of pressure, PV, that is pressure into volume, is equal to universal gas constant T into 1 plus B prime P C single prime P square D single prime P cube, where these are the same, that is a second, third and fourth virial coefficients, and these virial coefficients, they are characteristic of the gas in both cases. Of a gas, and it is temperature dependent. It is characteristic of a gas and it is temperature dependent, which we did not find for the van der Waals constants. So, we expect virial equation to be better than van der Waals equations, and that is all for this session. Thank you.